So in this video, I'm going to show you how to perform a regression analysis on SPSS and how to perform an ANOVA. And when we look at the output tables, I'll show you which things are important to report as well. All right, so let's take a look. I will also show you how to make a scatter plot in SPSS. So I'm going to go to a data set that I've created, and this data set is very similar to our data set from Project 1, where I looked at car length and mean car length for different kinds of owners, faculty, staff, and students. And I've added 2 more columns of data. I did more investigation on the faculty and staff car lengths, and I learned more about these guys, so I put some more data in. So I'm going to show you my variable view and show you which data columns I've added. So in addition to car owner, whether the owner is a faculty, staff, or a student, and the mean car length, I've added a 3rd column of data called the number of children. And I only looked at the number of children for faculty and staff. And so this is an ordinal because you have somewhere between 1, 2, 3, 4, 5, 6, 7, 8 children. It could be nominal. I'm not sure what kind of measure that is actually. And the staff title. I also got data on who were these staff people. Were they tenure track faculty? Were they affiliates? Or were they general staff? All right? Because I had some ideas about number of children and length of car owner, and perhaps the title that you have and the size of your car as well. I was thinking, of course, if you had more children, you would have a bigger car. And I was thinking if you were a staff, you might have a bigger car than a tenure track faculty, because tenure track faculty are less likely to have as many children. I don't know. That's what I was thinking. So I collected data for our 30, I had 30 car lengths for faculty and staff individuals. So I collected data on the number of children and the type of title the person had, okay? And I put all that data in. For the number of children, I simply entered the total number of children they had with numbers. For the staff title, a number 1 meant a tenure track faculty, a number 2 was an affiliate faculty, that's what I am, and number 3 was a staff member, a general staff member. So I have data. Now, the question is there a relationship between the number of children that an employee has and the length of the car that they have? It kind of makes sense, right? You'd expect people with more children to have bigger cars. So what we want to do is an analysis that is statistical analysis that compares, that looks for a relationship between 2 variables. Does the number of children one has predict the size of the car that you have? Does that make sense? We're going to do a regression analysis. And so we go to our Analyze box, we look for regression, and we look for a linear regression. Click on that, and I am going to, and I've already added these, I opened it earlier, that's why. My dependent variable will be the length of the car. The variable that I think predicts the length of the car would be the number of children. So does the number of children that one has predict the size of the car that you have? Does that make sense? Okay, and I'm going to just check here under options. Nah, I don't need any of that. So let's take a look at, is there a relationship between number of children and car length? We hit OK, and we get a huge amount of analysis popping out. What this model does is it looks at essentially a scatter plot. You look for a relationship in a set of data. And what the scatter plot does is it measures what's called an R value or an R square value. The R square and the R value help us understand how close to a line. Do all the data points fit in a nice line, or is there a lot of scatter? The higher the R value, the higher the R squared value, the more closely the data fit with the line. And so we're going to be looking at a couple of values when you report these data. You're going to report the R-squared value. You're going to say that we found an R-squared value of 0.653. And we do, what happens is the program does an ANOVA to ask, is this a significant relationship? Is there a significant relationship between the number of children that one has and the size of their car? And it does what's called an ANOVA to test for that relationship. And so what you want to also report is the ANOVA's F value. That's the statistic that the ANOVA reports. It's 52.7. The degrees of freedom, the total degrees of freedom, 29. And the p-value, or the significance. In the SPSS code, it's called significance. This is p less than 0.001 is how I would report that value. In other words, there seems to be a significant relationship between the number of children one has and the size of your car. Okay, that's fantastic. In fact, this R-squared value tells us that 65% of the variation we see in car length can be explained by the number of children someone has. So that's what that R-squared value actually means. 65% of the variability we see in car length is predicted by the number of children. So the number of children that one has is a strong predictor of the size of the car. And that's why our p-value is so small. The data support our hypothesis. Okay. Down here, you can, whenever you get a scatter plot, you can determine the equation of the line as well, the linear regression, and that would be equal to, y equals mx plus b. The m and the b here represent, the m is 0.374, that's the slope of the line, and the mx plus b, the y-intercept, is 4.0. So that's what those represent. So you could write y equals 0.374x plus 4.0 if you wanted to write the equation of the line. I want to see this in a graphical format. I want to see this relationship. So I'm going to graph. I'm going to perform a graph. And what I want to perform is, in fact, a scatter graph. Okay. And my scatter graph is going to show, let's see, I want to make sure I did this right. So I go down to scatter data, and I pick this one with a line here, and I bring it up to the open box. And I have to do a couple of things. I want to make sure that I'm looking at the mean car length on the y-axis and the number of children on the x-axis. And let's see, I probably want to make this a little neater looking. Number of children, the y-axis. Oh, sorry, it's yelling at me. I don't think this matters. The x-axis is the number of children. The y-axis is the mean car length. I probably want to write that a little bit in meters. Okay, and I can have all that. That's good. And I don't really want the title at all in there, so I'm going to click that off. And I think that's what I want it to look like. So now I'm going to click OK, and it should pop up in my output screen. Here's my graph. Okay, so I can kind of see this relationship between the number of children and the mean car length. I can kind of see that there is a positive relationship. The more children you have, the bigger your car. And we found that this relationship is significant. The number of children one has predicts the mean car length. We found that with the regression analysis. But I have one more question that I want to do, and so I'm going to go back quickly to our data. I also was wondering, is there a difference between different kind of employees? Tenure track faculty, affiliate faculty, and general staff with respect to their car size. So I learned about whose cars these were and what their title was. Again, I designated a title of 1, the tenure track, 2, the affiliates, and 3, general staff. And I want to compare the means of these three groups. What's the mean car length for the tenure tracks versus the affiliates versus the general staff, right? And I want to do a statistical test to compare the means of three groups. Now, I've done a statistical test to compare the means of two groups. I did a t-test. What would I do to compare the means of three groups? We do an analysis of variance, or an ANOVA. So, I'm going to analyze my data. I'm comparing means, but this time I'm comparing means doing a one-way ANOVA. And my the dependent variable is the length of the car. My factor will be what title the staff has. Is it general staff, is it tenure track, or is it affiliate? I have to check my options. I want to include descriptives here so that I can see the descriptive data. I want to see the means. I want to be able to compare them a little bit. I can also include what are called post hoc tests. I'm not sure if we'll use those or not, but I'm going to include what's called an LSD post hoc. And I'm going to hit OK. So here's what I get. I get first descriptive data. The descriptive data just will show me the tenure track, affiliate, and staff results. So I had 30 total. There's a little bit of a mix there. And their mean car lengths. It looks like staff have bigger cars than both the affiliates and the tenure tracks. But are these significantly bigger? That's what the ANOVA is going to tell me. I also can record the standard errors here. Well, when I look at the ANOVA is a statistical test with an F value, so we're going to have to report the F value equal to 7.25, the total degrees of freedom of 29, and the P value is 0.003. Yes! What that tells us is the differences we see are not just due to chance. In other words, there are some real differences between our three groups here. Yes, but which group is significantly different from each other? Are they all different from each other? Or are the staff different from the tenure track but not different from the affiliates? How do I know? That's when we do a post hoc test. And the post hoc test actually looks at each set of two groups and asks, are these significantly different from each other? So in this, we see the tenure track compared to the affiliates, and we get a significance level of 0.34. Tenure track and affiliates don't differ in their car size, but tenure tracks and staff have a p-value of 0.001. So staff have bigger cars than tenure tracks based on our means from before. And you can look at all of these relationships. I might want to do a graph again, and in this graph I would probably need to do a basic bar graph, okay? And I'd want to put my staff title as my x-axis, the independent. So we got tenure tracks, affiliates, and general staff. And my mean car length as the y-axis. And I would want to do a couple of things like get rid of the title. I don't like that. For the mean car length, I'd want to include the error bars, the standard error bars. Oh, this makes it by 2. I want to maybe make it by 1. There we go. So we have 1 standard error, not 2. And then for the x-axis, we call them staff title. Let's just write down title, I think is better. For the y-axis, oh, sorry, I don't know why it does that. And then for the y-axis, I might want to write down the mean car length. Mean car length in meters, like that. Something like that. I think we're ready to go. And then here's my graph. Mean car length, staff title. Oh, it didn't change our x-axis. For some reason, it didn't change that. But in any case, I've got all 3 of my sets of data. It looks beautiful. I can copy and paste this graph if I want to, and I can see that the staff tend to have bigger cars than the tenure track. My ANOVA showed me that this difference was significant. So that's how you would do an analysis of variance on SPSS. And I want to save, before I leave, I'd want to save my output, and I'd want to save my data file so that all of my group members can access it again, right? So save it so that it's available, to put it onto your group file exchange site on Blackboard or somewhere else where everyone can access it. Okay, I think that's everything, so I will stop.